So this next section deals with giving unique IUPAC names to not just alkanes, but cyclical alkanes. So if you have an alkane that forms a ring with its carbons, there are slightly different rules for naming those types of molecules. And again, I have this little chart here just for reference. Hopefully you have a little cheat sheet as well that you can refer to. The first rule is pretty straightforward. If you have a cyclical alkane, and I'll show you an example in a moment, and there is one simple substitution, one simple thing attached to the ring, then the substitution is the prefix and the ring is the suffix. And this is basically how you name your cyclical alkane with a substitution. And an example of that is shown here. So if you look, this is the part of the molecule that I'm circling here is a ring of carbon atoms. And if you count them up, we can count 1, 2, 3, 4, 5, 6 carbon atoms in the ring. So if there are 6 carbon atoms in the ring, this ring is like hexane, but since it's a ring, this is actually cyclohexane. And our cyclohexane has a substitution. The substitution is made of 2 carbons. There's one at this bend here, and there is one additional carbon at the very end that's drawn out. What that means is that the substitution is made of 2 carbons, and because it's made of 2 carbons, it's a little bit like ethane. So this is an ethyl substitution attached to cyclohexane. So the correct IUPAC name for this molecule, following the rule that I've shown you here, is that's cyclohexane. This is an ethyl substitution. The correct name for that entire molecule is ethyl cyclohexane. And that's pretty much it whenever you have a single simple substitution on a cyclical alkane like this. Now, you may be asking the question, which is a perfectly valid question to ask, don't I need a number in this name? Don't I need to say what carbon my ethyl is attached to? And when it's a single simple substitution like this, you don't. The reason that we need numbers when we were talking about the molecules like this one over here, the reason we need numbers is because you need to give a number to show where your substitution is relative to an end of the chain. So if your substitution is over here, you basically say, look, I'm at position number 2 relative to the left side of the chain. Or if it's over here, then you're talking about how close your substitution is to one end or the other end. But if you have a cyclical chain of carbons where they wrap around, there is no end. So if you just have one substitution, it doesn't really matter what carbon it's attached to because all of the carbons are more or less identical. They don't have a left end or a right end. They don't have a beginning and an end to the chain. It's just a circle. So it doesn't matter which carbon your substitution is attached to because all of the carbons are more or less identical, and because of that you don't need a number in these types of names. But this is only true if you have one simple substitution. It gets a little bit more complicated if there's more than one simple substitution. If there's more than one simple substitution, you list each one in alphabetical order, and then you give each one a number in the ring. So you number the carbons in the ring and you say what position in the ring your substitutions are located in relative to the other substitutions. And the way that you number the carbons in the ring, you are supposed to minimize the sum of all of the numbers in your name. And I'll show you a couple of examples of that, starting with this molecule here. Again, we look at this molecule here and it contains a ring with 6 carbons in it. 1, 2, 3, 4, 5, 6 carbons in the ring. These other carbons over here and over here, they are technically not part of the ring. They're considered substitutions. So 6 carbons in the ring means that this ring is a cyclohexane ring, and then we have 2 different substitutions. This substitution up here is made of 2 carbons, 1 carbon at this bend and 1 carbon at the very end. That means that this is an ethyl substitution. This substitution over here is just made of 1 carbon. Because it's made of 1 carbon, it's like methane. This is a methyl substitution. So now we have to number the carbons in the ring to give us the appropriate name. So we can number them using the red numbering system here. We could number clockwise, basically, and start at the ethyl substitution, call this carbon 1, this one carbon 2, etc., all the way around. Or we could number in reverse. We could number counterclockwise, which is shown with green numbers. We could call this one carbon number 1, this one carbon number 2, and go counterclockwise until we reach the other end of the ring. And then basically we have to pick whichever one minimizes the total number. So and we have to list our substitutions in alphabetical order. So the name of this molecule is going to be something, something ethyl, something methyl cyclohexane. And another way of writing it is it's going to be X ethyl, where X is some number specified by us numbering the carbons in the ring, dash Y methyl, and the Y is going to be whatever other number that the methyl group is attached to, dash cyclohexane. So we have two possibilities here. We could either number our molecule as 2-ethyl-1-methyl, that's using the green numbers, because in using the green numbers, this ethyl substitution is at position as at carbon number 2, and this methyl substitution is at carbon number 1. So we could call it 2-ethyl-1-methyl cyclohexane. Alternatively, we could use the red numbering system, and we could say that the ethyl substitution is at carbon number 1, and the methyl substitution, this one over here, is at carbon number 2. And the idea, one of the rules, is that you're supposed to write out every possible name and figure out which one adds up to the lowest number. And over here, 2 plus 1 is 3. And over here, 1 plus 2 is also 3. So that rule doesn't really help us in this case because both of the numbering systems that I picked, they both add up to 3. And there are actually many other ways to number the carbons in this ring. You don't have to necessarily start with this being carbon number 1 or this particular carbon being carbon number 1. But every other possible numbering system is going to give you a much larger number than either of these names. And these only add up to 3. All of the other ways that you could number these carbons would add up to more than 3. So I'm only focusing on these two names because they actually add up to the lowest numbers. However, there's a tie, right? They both add up to the number 3. So the way to break the tie is that basically you have the number 1 come first. You have the lowest number come first, and since these are listed in alphabetical order, ethyl comes before methyl because E comes before M, and since there's a tie, you pick the name where the number 1 comes first in the name as well. So this particular molecule should be called 1-ethyl 2-methyl cyclohexane, and actually there should not be a dash here. It should just be all one word, methyl cyclohexane. But hopefully you get the picture here. The correct name for this particular molecule is 1-ethyl 2-methyl cyclohexane. There will be a more complicated problem on the next slide. So on this slide, you can pause at any point. The rules are up here for naming substituted cycloalkane molecules, and this is a relatively complicated cycloalkane, and it has 3 substitutions. So if you want, you can pause and try to name this thing. It has a chloro substitution down here, this is a methyl substitution up here, and this is an ethyl substitution up there. And again, the idea is the trick here is to figure out what numbers you are supposed to give to each of the carbons in this ring. And again, this ring has 6 carbons in it, so the end part of the name is going to be cyclohexane. But our job is to figure out what numbers to give each carbon. And I'm going to show you a relatively complicated picture. I picked 4 different ways to number the carbons in this ring, and they are color-coded. But the idea is that each time I either numbered this particular carbon over here as carbon number 1, and I either went clockwise or I went counterclockwise, or I picked this particular carbon as carbon number 1, and again I either went clockwise in numbering the other carbons or I went counterclockwise in numbering them. The reason why I picked those is because these are closest together, so my guess is that when the ultimate name is chosen, numbering this one number 1 and this one number 2, or vice versa, that will probably give me the minimum the minimum sum of numbers in the name. So there are many other possible combinations, but these are probably the best guesses that we're going to have. So again, in red, I am numbering, calling this carbon as number 1, and I'm going clockwise. In green, I'm calling this one as carbon number 1, and I'm also going clockwise. In blue, these blue numbers, I call this carbon number 1, and I go counterclockwise. And in pink, I call this carbon number 1, and I go counterclockwise. And so it's going to be, the name of this particular molecule is going to be blah, 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 cyclohexane. Or maybe with a little bit more detail, it's going to be X-chloro. So here's our chloro. The reason that chloro comes first is because we have to list the substitutions alphabetically. And there is a chloro substitution, a methyl substitution, and an ethyl substitution. So the beginning part of the name is going to be X-chloro, where X is whatever number the chlorine is attached to, whatever number carbon the chlorine is attached to. Y-ethyl, because ethyl comes next alphabetically, and Y is going to be whatever number we end up picking for the carbon that the ethyl is attached to, and Z-methyl, where Z is the number of the carbon that the methyl is attached to, and then cyclohexane. So let's write out the possible names. Here are the 4 possible names using the numbering systems that I've picked here. And I've sort of tested this more exhaustively, but it'll be kind of crazy to do every possible numbering system. So in green, using the green numbers, the chlorine is actually on carbon number 3, because there's number 3 in green. It would be attached to carbon number 3, and if we use the green numbering system, the molecule would be called 3-chloro-6-ethyl 1-methyl cyclohexane. And if we add up the numbers, 3 plus 6 is 9, plus another 1 is 10. So whatever this particular name, the numbers add up to 10 in that name. Let's use the maroon colored numbers, so they're shown in the inside of the ring as well, going clockwise. If we use the maroon numbering system, the numbers would be the name would be 4-chloro, because now the chlorine is attached to what we are calling carbon 4. 1-ethyl, because the ethyl is attached to carbon 1. 2-methyl, because the methyl is attached to carbon number 2, cyclohexane. If you add those numbers up, it's 4 plus 1 is 5, plus another 2 is 7. So we've got a low number there, and if you scan along, you can see that the blue numbering system is the worst. So going counterclockwise in this direction, our name would be 4-chloro, 1-ethyl, 6-methyl cyclohexane, but 4 plus 1 is 5, 5 plus 6 is 11, and this one is definitely the wrong answer. 7 here, this name beats out number 10 as well. And then the pink numbering system, starting here and going counterclockwise, the name would be 5-chloro, 2-ethyl, 1-methyl cyclohexane. 5 plus 2 is 7, 7 plus 1 is 8. So this one loses as well to the maroon colored name. So the maroon colored numbering system is the correct numbering system to use. If we use the maroon colored numbering system, we start by calling this particular carbon number 1, this one number 2, 3, and the chlorine is attached to number 4. So the correct name, the correct IUPAC name, which is an unambiguous name for describing this particular molecule, is 4-chloro, 1-ethyl, 2-methyl cyclohexane. So I know that this is probably somewhat difficult and a little bit strange, but I think you will ultimately get used to it. All of these naming rules, they might seem like a lot at the beginning, but if you practice a little bit, you'll see that they're pretty straightforward and pretty simple. And so this is the end of sort of the discussion about giving unique names to organic molecules.